When writing equilibrium expressions, we will generally follow the formula that we got from the last video. If you have a general balanced chemical equation that is reversible, all you need to do to write the equilibrium constant expression is write down the letter K, write down an equal sign, use brackets to indicate molarity for each individual chemical, and put the stoichiometric coefficients as powers. Now let's practice on a slightly more real example. Let's use one of my favorite chemical equations. In this case, this is labeled as a homogeneous situation because all of the chemicals in this equation are gases. In this case, every single chemical participates in the equilibrium constant expression. Alright, K equals concentration of ammonia squared divided by nitrogen with an invisible 1 as the power, hydrogen gas cubed. Let's do one more example for the homogeneous category. Iron 3 plus, aqueous, plus a fun but stinky friend, also aqueous, yielding a really cool complex ion, also aqueous. In this case, we'll write the molarity of this cool complex guy divided by each individual reactant and there you have it. That's how you write equilibrium expressions for homogeneous scenarios. For heterogeneous scenarios, we'll usually see equations that involve solids and gases or solids and aqueous species. For now, let's just focus on solids and gases. According to the rules for equilibrium, and honestly for chemical reaction speeds in general, if you have the choice between including a gaseous molecule or a solid, you're only going to include gases because they have the freedom and the mobility to be able to have enough kinetic energy to effectively cause collisions in reactions, blah, 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 blah. Basically, you only put gases in equilibrium expressions. You do not put solids or liquids. If you stick to this rule, you will always do these correctly. Let's do one more example. In this example, I have 3 different gases I need to include in my expression. So that's UF6, water vapor, and HF. Again, for heterogeneous equilibria, please make sure you never write down a solid or a liquid. And now for equilibrium involving pressures. Just so that you feel comfortable, including pressures is a way to control these. make sure you remember our gas laws. If you rearrange PV equals nRT so that the moles are divided by the liters, you can see that concentration, or molarity, is directly proportional to pressure. This validates our use of pressure in equilibrium problems. But so we don't get confused as to what units we're using, we need to use different letters. If we have an equation like the one we were using before, with the hydrogen gas and the nitrogen gas yielding 2 ammonias, we can write the equilibrium constant's pressure version by including the partial pressures of each individual species instead of their concentrations. We can write that using parentheses for pressures, by using a large P to indicate a partial pressure, and the subscript of the chemical itself so that we know which partial pressure we're talking about. You still need to follow the pattern of using the stoichiometric coefficients as the exponents. I would also like to point out at this point that you need to remember that in every single one of these equilibrium expressions, the concentrations are multiplying times each other. Sometimes my students accidentally put an addition symbol here and it really throws off their calculations later. Make sure that you practice enough of these that you won't make mistakes later. They are always the first step in every equilibrium problem.